Hi everyone. Note 7.2 are on geometric sequences, which is a continuation from what we did in note 7.1. So for a geometric sequence, it's a sequence that has a common ratio. So this time, instead of adding the same number, we're multiplying by the same number, okay? So it has so multiplying by the same number. Okay, each term is found by multiplying by the common ratio. Okay, but one thing, remember the common ratio is allowed to be a fraction, okay? Because sometimes the numbers will be getting smaller instead of getting larger. So in question number 4, the series or the sequence that we're given is 9, 8, 18, 36, 72, so on and so forth. So what this is saying is, when my term number, which is, we always use n for a term number, is 1, our actual term is 9. When our term number is 2, our actual term is 18. When our term number is 3, our actual term is 36. Fourth term will be 72, so on and so forth. And if you guys notice, this should look like an exponential graph if I were to graph it out, okay? But because it's discrete, it's going to actually end up being just single dots where we don't actually connect our dots, okay? But it still will follow an exponential look. So is this a geometric or arithmetic sequence? Well, it's geometric because we have a common ratio right here of 2, because to go from 9 to 18, you multiply by 2. To go from 18 to 36, you multiply by 2. To go from 36 to 72, you multiply by 2. So we're going to say it is geometric because it has a common ratio of 2. Okay, then it asks us to write the next 3 terms of the sequence. So if we have 72, to get to the next term, I'm just going to multiply that by 2, and I get 144. So that's the next term. Then I'm going to take 144 and multiply that by 2, and I end up getting 288. So that's the next term. Okay? And then to find the last term, I'm going to take 288, multiply that by 2, and I get 576. So those are the next 3 terms of the sequence. So question C asks us to write the recursive formula for the sequence. So recursive means, remember, recursive means it's based on the previous term. Okay, so essentially what we are saying right here by saying t sub n, so this is saying the term that we're looking at is equal to the previous term. So I'm going to take the previous term, which is t sub n minus 1, and I'm going to multiply that by 2. Because that's what we did. We took our previous term of 72 and multiplied it by 2, which we got 144. We did the same thing with 144 to find the next term, and we did the same thing with 288 to find the next term. But if I do it this way right here, then it has to have t sub 1 is defined. Because if each term is based on the previous term, I have to know where I'm starting. And since t sub 1 is 9, I'm going to define t sub 1 equals 9, and also n has to be an element of the natural numbers. Okay, so then for question D, it says write the recursive formula for any geometric sequence. So essentially, it just is going to say that this current term is equal to the previous term multiplied by the common ratio. So here, R is the common ratio. Okay, where t sub 1 is defined, so you need to make sure you define t sub 1, and n is an element of the natural numbers. Okay, and then question E asks us to write the general rule for the sequence. If you remember when we did exponential functions, it was always y equals a times b to the power of x, where a was our initial value and b was our growth rate. Okay, here instead what we're going to do is we're going to say pretty much the same idea, except we're going to say t sub n is equal to, our initial value right here is going to be the first term, so it's going to be t sub 1, times our growth rate here is our common ratio, so it'll be r. And instead of having it to the power of x, it should be to the power of n. But there's one key thing that's really important right here. This a always happens when x equals 0. But here, this is when our independent variable is 1, which means that there's a shift of 1 to the right. So this should be minus 1. Okay? So that's the general rule that we should do right here. So I apologize. Question F, write the general rule for any geometric sequence. That's going to be this rule right here. So this is going to go down here. And for this question up here, instead of r, we'll actually replace the r with 2. So it'll be t sub n equals t sub 1, which is 9, because it's our initial value, times 2 to the power of n minus 1. So let's just check to see if this works. So right here, we have that our fourth term is 72. So to find, let's do a quick check right here. To find t sub 4, I'm going to do 9 times 2 to the power of 4 minus 1. So I get 9 times 2 to the power of 3, which is 9 times 8, which is 72. Now that should make sense to you, because essentially all we're doing is to go from 9 to 18, we multiply by 2. So I'm going to take 9, multiply by 2. That's going to be to get to our second term. To get to our third term, we multiply by 2 again. Notice how there's two 2's here. To get to our fourth term, we multiply by 2 a third time. So every time we're getting to our next term, we're multiplying by the common ratio one less time than the term number that we're looking at. So that's what this is saying. You take 9, multiply it by 2, n minus 1 times. Okay. So question number 5 asks us to figure out how many terms there are in the geometric sequence that's given right here. So here's the first term. This is t sub 1. This is t sub 2. And this is t sub n. We don't know how many terms there are. So first thing I'm going to do is figure out what the r value is. And the best way to find the r value is to, so let's write this down. To find r, the best way to do it is to divide the following terms. So we'll do t sub n divided by t sub n minus 1. So basically one term divided by the term that came before it. So right here, I'm going to find r by taking 17,537,553, and I'm going to divide that by 52,612,659. And when I go ahead and divide those two values right here, I end up getting the following answer. I end up getting 0.3 repeating, which we know should be 1/3. So here r is equal to 1/3. So now that I've done that, I'm going to find an equation, because my equation has n in it, and I want to know what n is. So here what I'm going to do is I'm going to say t sub n is equal to t sub 1, which is 52,612,659, times r, which is 1/3, and because it's a fraction, it needs to be in brackets, raised to the power of n minus 1. Okay, now that I've done that, I know that t sub n is equal to 11. So I'm going to fill that in for t sub n here to solve for n. So I get 11 equals 52,612,659 times 1/3 to the power of n minus 1. Now, one option I have is to solve this algebraically. So if I were to solve this algebraically, I would divide both sides by this 52 million number right here. So I end up getting 11. I'm going to leave it as a fraction. 11 over 52,612,659 is equal to 1/3 to the power of n minus 1. And if you remember, we learned that to get the exponent out of here, I can log both sides. So then when I end up logging both sides, it's going to say the log of 11 over this 52,612,659 is equal to, don't forget, we log to bring this n minus 1 out in front. So n minus 1 times the log of 1/3. Okay, so then in order to solve for n right here, I want to get rid of this log of 1/3. So I end up getting log of, again, this big ugly fraction, and I'm going to keep it this ugly fraction for now until I actually get to a point where I can deal with it a little bit more easily. Okay, over the log of 1/3 is equal to n minus 1. So I'll go ahead and do some calculation now, okay? So when I type it into my calculator, I'm going to type in 11 divided by 52,602,659. Press enter, I get 2 times 10 to the power of -7, so I get a tiny, tiny number. But I'm going to take the log of that number, and then I'm going to divide it by the log of 1/3. So I'm going to type in 1/3 and then press log. Some of you guys in your calculators, you can type log of the number. In this calculator, I have to type the number and then log it. Press enter. I know that this is going to be 14. So here I get 14 equals n minus 1. Therefore, n equals 15. Okay, so therefore, the term, or this sequence has 15 terms. Okay, now I want to show you how you could do this on Desmos. So the first thing that we're going to do is I'm going to see what it's going to look like in a table. So I'm going to have a table of values right here. And we've got x1, and we're just going to go by ones because these are the terms in our sequence right here. Okay, and then after a while it'll start to autocomplete. Let's go to like about 30 because at this point in time I'm pretending like I wouldn't have known the answer. And to find the term, I would take 52,612,659. If you notice right here, I'm just going to use my equation right here that I got right here, times 1/3. So in bracket, I'm going to type 1/3 right here, close my brackets, to the power of whatever this value is here. So since this list is called x1, I'm going to type in x1, but I'm going to put it in brackets so my calculator knows that this entire thing is my exponent because I still have that -1. And then when I press enter right here, I have my list of values. So I can just go through and look at my list of values until I get to 11. And if you notice, 11 happens when n is 15. Okay? And then another option is to graph out the line y equals 11, and I can see where it's going to intersect right here. Now, if you notice, the values at the beginning are huge, but it's starting to get smaller and smaller, and here is that exponential picture that we were talking about. This is how it ends up looking exponential, and this happens at 1511, which means that there are 15 terms in the sequence because this is the last term right here. We don't even have to worry about the remaining terms. All right, the last thing we need to do is just fill in the recursive formula and the general term for geometric sequences, and then we'll be good to go. So the recursive form is going to be t sub n is equal to the common ratio times the previous term, where n is an element of the natural numbers, and r is the common ratio here. And then our explicit formula is going to be t sub n equals t sub 1 times r to the power of n minus 1, again, where n is an element of the natural numbers. Okay? All right, that's it. Let me know if you have any questions. Have a good day. Bye.